Today we will learn Green's theorem. Green's theorem has two forms. One is normal form, the other one is tangential form. Normal form states outward flux of a field across a simple closed curve is equal to the double integral of the flux density of the field over the region enclosed by the closed curve. In notations, we can write integral over C f dot n ds. That means outward flux of a field across a simple closed curve, which is equal to double integral over r divergence, that is flux density is divergence of f dA. If I represent capital F is equal to mi plus nj, which is a field capital F, then I can rewrite this integrals as integral over C m dy minus n dx, which can be written as equal to double integral over r del dot f. I can write it as m suffix x plus n suffix y, partial derivatives with respect to x and y, dx dy. So to verify Green's theorem, normal form of the Green's theorem, we have to check the LHS and RHS separately, and we have to check whether it is equal or not. In the similar way, we have tangential form as well, which states that counterclockwise circulation of a field around a simple closed curve in plane equals the double integral of circulation density over the region enclosed by the closed curve. In notations, I write integral over C f dot TDS, which represents the circulation, which is equal to double integral over R, and the circulation density is the curl dot product with the normal to the region, that is del cross F dot K, because R is the plane in XY, so normal to with the R will be K, unit normal, that is into dA. Similarly, if I represent capital F as mi plus nj, I can rewrite this as integral over C f dot TDS can be written as m dx plus n dy, which is equal to double integral over r del cross f dot k. I can write it as, after calculation you will get nx minus my dx dy. So to verify the tangential form, we have to find the LHS and RHS, and we'll check whether it is equal or not. So to verify Green's theorem, both forms we have to verify. So to verify normal form, we have to find the outward flux of the field, and you have to find the flux density. And to verify the tangential form, you have to find the circulation of the field around the curve, and you have to find the double integral of the circulation density. So we will find both sides, and we will verify whether the theorem is satisfied or verified or not. So let's see one problem to verify Green's theorem. Solve this problem. Question: verify Green's theorem in the plane for integral over c xy plus y square dx plus x square dy. C is closed curve of the region bounded by y equal to x and y equal to x square. Here we have to check which form of the Green's theorem we have to use. This given integral is of this form: integral xy plus y square dx plus x square dy. Means there is a term with dx and dy. If we take this as m and n, it is matching with Green's theorem tangential form. So you can see the tangential form here. So you can use this form to verify the Green's theorem in this context. So let's write the statement once again. So by Green's theorem you have integral m dx plus n dy equal to, so over C is equal to double integral over r nx minus my dx dy. So first of all we have to find the region and C. So let's draw the curve that is given, that is the region bounded by y equal to x and y equal to x square. So let's draw the axis first, and y equal to x the line that passing through the origin. So we have the axis and the straight line. So this is x-axis and this is y-axis and this is y equal to x line. And next curve is y equal to x square, which is a parabola. So let's mark the point 1 and this one. So this is 1.1, and this parabola will meet the line at 1, 1. So almost draw in this way. Okay. So our region of integration is this part. Here, to get the limit for integration of the double integral, that is the region R, we have to go for y limit and x limit. Let's first find y limit. You can go in two directions, either in the direction of y or in the direction of x. So here I am going to choose direction of y. So I will choose this direction first. So in this region, it starts from this curve, that is y equal to x square, and to the curve y equal to x. So your y limits are starts from x square to and its end in x. So everywhere in this region, it is starting from x square and it is ending in x. So you can take your y limit as x square to x. And this entire region is lying from x equal to 0 to x equal to 1. So your x limit, you can take it as 0 to 1. So for this region R, you can take the limit of integration of x and y as this. Now for C is a closed curve that starts from the origin O and end over here in A and will come back to O again. So you have two paths, one along the parabola y equal to x and the other along the line y equal to x. So let's divide this closed curve C into two integrals. The line integral can be found by finding the integral over OA plus integral over AO. So to find the line integral, you have to go for the parameterization of the curves, and for the curve y equal to x, you can take the parameterization as x is equal to t and y equal to t, and t varies from 0 to 1. We can use the usual methods to find the parameterizations. And for the curve y equal to x square, we can take the parameterization x is equal to t, and if you give x equal to t, you will get y equal to t square. And similar way, to get the portion of the curve, you have to give 0 less than or equal to t less than or equal to 1. And remember one thing, your curve has a direction. OA direction, you have 0, 0 to 1, 1. So, for this curve, your integration limit should start from 0 to 1. But for the other direction, it is starting from 1, 1 to 0, 0. So your point should start from 1, 1 to 0, 0. So you have to give the limit of t from 1 to 0, not 0 to 1. So you have to consider the direction in which the curve is going. So first is OA and the other one is AO. Now let's move on to find the LHS and RHS of the theorem. First, RHS equal to double integral over R nx minus my dx dy. Let's find what is n. Here n is x square and m is xy plus y square. So n is x square. So you can find nx. Nx is equal to 2x. Then m is equal to, let's see, xy plus y square. xy plus y square. Let me see once again. Xy plus y square. So m y equal to partial derivative with respect to y. So x plus 2y. Now let's give in the interval equal to, as we found the integral limits, y limit will give first, that is from x square to x, and x limit is from 0 to 1. That's in the last slide we have seen. This is the limit of integration for your r. So I have given that. Then nx is 2x minus my is x plus 2y dx dy. So let's find this integral. This is equal to integral 0 to 1 integral x square to x. Let's subtract, you will get x minus 2y. First we'll integrate with respect to y because the limit of integration is with respect to y first, then dx. So let's do this nested in integration. This is equal to integral 0 to 1. With respect to y it is, so xy minus y square will come within the limit x square to x dx. So this is equal to integral 0 to 1. You will get x square minus x cube plus x raised to 4 dx. So x square will get cancelled, and the remaining, if you integrate, minus x raised to 4 by 4 plus x raised to 5 by 5 within the limit 0 to 1. So this is equal to, you will get minus 1 by 4 plus 1 by 5, and the rest of that will be 0. So this is equal to, you will get minus 5 plus 4 by 20, that is minus 1 by 20. So this is the answer for your RHS. Now we have to check the LHS, and we have to get the same value to verify the Green's theorem. LHS equal to integral over C m dx plus n dy. Here we have split this integral into two, that is integral over OA plus integral over AO. Let's find the first one, integral OA ms, m value, let's see the m value is xy plus y square, it is xy plus y square into dx plus ns x square, that is x square dy. And along OA we have seen the parameterization, that is This is the parameterization along OA. This one is OA, that is y equal to x square, that curve. So the parameterization is x is equal to t and y equal to t square, and t is 0 to 1. So let's give that values. Integral t value is 0 to 1, the limit 0 to 1, and x is equal to t and y is equal to t square, plus y is t square, so you can t square whole square, that is t raised to 4, and dx. Since x is equal to t, dx will be equal to dt, and y equal to t square, then dy is equal to 2t dt. So let's here plus, this is dt, plus x square, that is t square, into dy is 2t dt. Now let's integrate this. This is equal to integral 0 to 1. This is t cube plus t raised to 4 plus 2t cube. That is 3t cubed dt. Equal to integral 0 to 1, 3t cubed plus t raised to 4 dt. So which is equal to, let's integrate 3t by 4, t raised to 4 by 4 plus t raised to 5 by 5 within the limit 0 to 1. That is equal to 3 by 4 plus 1 by 4. Sorry, 1 by 5. 1 by 5, which is equal to, if you add, you will get 16 by, so 16, no, so calculate this, 15 plus 4 divided by 20, that is equal to 19 by 20. Now we have to find the other integral, integral AO. Integral AO, again you have to go for m dx plus n dy, which is equal to, here you just remember this line AO in this direction, so you have to start from 1 1 to 0 0. For this you have to give the integral limit from t equal to 1 to 0. So remember that, and we will give the limit accordingly. So you have to give from 1 to 0, and that is along the straight line y equal to x. So the parameterization is y equal to t, x equal to t. So let's give the parameterization. So y equal to t, x equal to t. So m is equal to, we know m is equal to xy plus y square. So xy plus y square dx plus x square dy. So instead of the limit, we will first write AO, then after substitution we will give the limit. So this is equal to integral, now 1 to 0, instead of x and y we will give t, so t square plus t square dx is same as, because x is equal to t and y is equal to also t, you will get dx equal to dt and dy is also equal to dt. So dt plus t square dt again. So this is equal to t square 3 times. So integral 1 to 0, 3t square dt. This is equal to 3t cube by 3 within the limit 0 to 1. So this is equal to, you will get 1. Now to find the integral over c that m dx plus n dy. We have to add, this is not 0 to 1, excuse me, this goes from 1 to 0. 1 to 0, so this will be minus 1. So we have to add now integral OA plus integral AO. So this is equal to, first integral we have got 19 by 20 minus 1. So this is equal to minus 1 by 20. So this is your LHS. So LHS equal to minus 1 by 20, and previously we have got RHS as minus 1 by 20, means LHS and RHS are equal, hence our Green's theorem is verified. The tangential form, that is clockwise circulation of a field around a simple closed curve, equals double integral of circulation density of the region enclosed by the closed curve. So remember one thing, to find the line integral, you have to consider the direction and you take the parameterization to find the line integral, and on the other side, to find the limit of the integration of R, you have to, or of the region R, you have to draw the region and you take the curve accordingly, and you have to find the limits of x and y of the region, and then find RHS and LHS, and hence verify whether it is equal or not. Hope you have followed my session, and thank you for listening to me.